So thank you all very, very much for coming, and welcome to the 2024 edition of the Festival for Astronomy and Space. I'm seeing lots of familiar faces here, but for those of you who've not come to one of these before, this is basically our annual opportunity to give something back to the community and to talk about the great work we do here. And that's what this is all about, essentially. So tonight we have two wonderful talks for you. We've got Duncan, who I'll introduce shortly, and then we've got Shashir as the second act. The schedule is loosely that they'll both talk for between 45 minutes and an hour, maybe a bit less if they get excited and talk too quickly like I used to do as a kid, maybe a bit more if you have lots of questions. After each talk, we'll have some time for questions and for the handover. We do have microphone runners, so given that we're running this online and in person, we'd ask that when you've got a question, you wait for the microphone to reach you. That way the people online know what's going on. I'd also like to acknowledge that we're on land that has been home to astronomers for more than 70,000 years. And this blows my mind. You can probably tell I'm not originally from Australia. Where I grew up, we had 1,000, or maybe if you really push it, 2,000 years of astronomical history and heritage. So moving here as I did in 2010, it blew my mind to realize I was on a continent with a continuous history of astronomical knowledge and research and study, stretching back for at least 70,000 years, and current research is hinting it's closer to 100,000 years. So the traditional owners of the land, the Indigenous Australians, were the first astronomers as far as we can tell. And it's a real privilege for me to be on that land, to get to learn a little bit of their knowledge and wisdom through my time here, and to be part of that great journey. So I'd like to pay my respects to elders past, present and emerging, both from the local people, the Gayabal and Jarawai people, but also for the many countries across this incredible continent. Tonight's first talk is my colleague Duncan. So we've got a UniSQ clean sweep here. It's all local talent, and that's how great we are here. We've got to fly the flag. Duncan's a really good example of that. And I'll let him tell you about himself and what he does, because you're here to listen to him, not me. So over to you, Duncan. Thank you.
Thanks, Tess. Thank you very much, Jonty. I do get a little bit excited, and so I may talk fast, but I think I had something like 70 slides and cut them down to about 40, so I think that'll work out about right. I'm going to take the lid off because it's dark enough in here that this will probably be visible anyway. But I actually have a few toys up the front here that I invite you to play with on the way out. I think it's pretty cool to have a thermal infrared imager, even if it is a little handheld one. So give that a try on the way after my talk and after Shashir's. I'm going to be using some of these things as I go through my talk. But today I'm going to be talking to you about astronomical space instrumentation. I am an astronomer here at UniSQ. I also teach some of our undergraduate classes. I can see a couple of our undergraduates here today. But also I run our observatory, which is about a half an hour south of here. That's Mount Kent Observatory. And I am lucky enough at the moment to be involved in a couple of space telescope development, small space telescopes. So I'll mention those towards the end of my talk as well. But today I'm going to be focusing on space instrumentation, as well as a little bit about what we have learned from some of our our largest and most expensive, but also most impressive space instruments that NASA and ESA have launched over the last well, actually 30 years. Hubble's been going for a long, long time. I've got a model telescope here I'll refer to as well, and a few other bits and pieces. But I think that's probably enough. I am going to be running on two computers here because the fantastically complex system we have here won't allow me to run like I normally would. So every time I go forward on one screen, I'm going to have to go forward on the other screen. And whether I remember to do that or not, we'll see how we go. Okay, so I guess I will get started. So why space telescopes? Why do we go to space at all? We can build telescopes down here on the ground. In fact, we have some, as I said, at Mount Kent, not too far from here. But why do we want to go to space? Well, the main reason, the main driver for us to go to space is to get away from our atmosphere, the atmosphere around the Earth, and to be able to observe wavelengths that we can't see through our atmosphere. So those things seem fairly obvious, but let me just give you a few images and a bit more information about that. So this is a little video that should be on repeat. Sorry about the sound. It's an image of Venus through a ground-based telescope, and what you can see is that moving around. That moving around is the atmosphere above the telescope jiggling around and essentially moving the image slightly. It's the same sort of movement that gives us the stars twinkling, scintillation. So this effect makes it really hard for us to get the sharpest images that we want. Now, it's actually fair to say that we have a way around this now. We have some fantastic technology called adaptive optics, but it is very expensive and very complex, so we save that for the very largest of telescopes. This image was captured with a small telescope by an amateur, but it is a really nice image of Venus, but it does suffer from the effects of the Earth's atmosphere. So the Earth's atmosphere is one reason why we want to get away from, to go to space and get through our atmosphere. But the other reason is all of the different wavelengths of light that we want to observe. Now, if you get a little concerned about this, I'm going to spend a bit of time going. That image we were looking at was showing you about the different wavelengths of light and what we can see through the atmosphere and what we can't. I do have a laser pointer here, though I'll try and minimize my use of it because it's not going to show up on Zoom. But you can see in the center here, we have our rainbow spectrum. That's visible light. That is the colors that we see with our eyes. Our eyes probably evolved in water with our predecessors billions of years ago. In water, visible light can travel through water. That's why in the very deepest of oceans, you have anglerfish and all sorts of animals that use light as a lure. So normal light, what we call visible light, can travel through water, and early eyes in creatures were developed in water. So we are sensitive to visible light. But also the air is transparent to visible light, but it's not transparent to lots of other light. For example, you can see here to the right of the rainbow, we have wavelengths that are shorter than visible light. Now, I'm going to talk about what visible light is made up of very soon, but I will also talk about it as having wavelengths. Now, shorter wavelengths are things like ultraviolet. We know that, it gives us sunburn. When we go further to shorter wavelengths, we get down to X-rays and then gamma rays. These are high energy waves that are able to penetrate through materials. But they don't penetrate through our atmosphere very well. We're not, even though our sun is emitting in UV, we have various molecules in our atmosphere that absorb that UV and protect us from it. The atmosphere is transparent in the visible and a little bit further to the infrared. It's also got a very large gap in the radio, which is fantastic for us to do radio astronomy from the ground. So we do have a lot of radio astronomy here in Australia in particular, working at wavelengths that are much, much longer than the visible wavelengths that our eyes see at. That is the wavelengths that are meters long. So the other thing I wanted to discuss is what is light. The reason I want to discuss this is if we want to look at things far away, we can't go to a star system that's far away. It's just the distances are too vast. So we have to look at what's coming from those distant objects. And one of the main things that's coming from those distant objects is light. I will talk at the very end of my talk about a few other ways we can sense distant objects, but by vast majority, it is light. So we need to understand what this light is so we know how to build our instruments so that we can detect this light in different wavelengths and understand the objects and why they're emitting this light. So what is light? Well, light is made up of electric fields and magnetic fields. They're actually oscillating magnetic fields. You know what a magnetic field is, you've been near a magnet, and you know what an electric field is in the sense that that's the thing that drives electricity through all of our wires. But a photon is an oscillating electric and magnetic field. Now, that doesn't really make a lot of sense to us conceptually, but these sort of waves as they're being shown here, the yellow one going up and down and the pink one going sort of horizontally, the electric field and magnetic field, they're perpendicular to each other. The amplitude here is actually saying the electric field is stronger here, and then when it goes down, it's where the electric field is in the opposite direction, and the same thing for the magnetic field. This is one description of a photon, a light wave that is traveling through the universe. Now, I just did something that's a little confusing. I called it a photon. A photon is a particle. Waves have this complex situation where they are both a particle and a wave, and we're drawing them here as an oscillating an electric and magnetic field as a wave. Now, because they are a wave, They also have a property of a particle, but they are a wave. That means they have a wavelength. What does this wavelength mean? Well, this wavelength that I was just talking about a little bit earlier, some wavelengths can penetrate through the air, some can't, some can penetrate through water, some can't. This wavelength actually gives us the energy in the particle that is the photon. We can increase the intensity of the light, and that means we've got more particles, but energy per particle is set by the wavelength. So when we increase the brightness of something, we're having more particles coming from that object, so it is more, so it appears to be more luminous in whatever wavelength we're looking at, but the wavelengths actually set the energy of the particle. So what I've got here is a very simple diagram showing, which one's this? The one I'm after. A long wavelength particle up the top, medium, and a short wavelength. The short wavelength particle would have more energy. So I'm trying to sort of give you the idea that light has different properties depending on its wavelength. So once we've got that, we can then go back to this image and say, okay, we know a little bit about what light is, and we know all sorts of things in the universe are emitting light. So how can we observe it? And we can see here again, as I was saying before, from the ground, we can observe visible light very easily all the way up through the atmosphere. So I didn't maybe introduce the gray part here, but what we've got is the gray part is saying that this light is blocked by the atmosphere. And you can see that there's another gray patch here saying it's blocked. And as we go from the right to the left, we're going from short wavelengths to long wavelengths, and visible somewhere in the middle in this diagram. We're actually going through a logarithmic scale, so there's a very big difference in lengths. So we can look in the visible and we can look in the radio, and there's a little gap here in the thermal infrared that is also visible. That's an interesting one. Thermal infrared you might think of as heat seeing, and that's because all objects that are warm are emitting light. I'm warm right now, I'm emitting light, but I'm emitting light at a thermal infrared wavelength. That's what this camera over here sees. And so last night I took an image of my cat. First, I'm going to talk about different wavelengths. That's all. The cat's image coming up. Sorry. First, I was going to say there are different wavelengths. So this is when we do go to space, there are benefits to looking at the same object in different wavelengths. The objects look different at different wavelengths because they might have high energy particles whizzing around in them, electrons being accelerated by magnetic fields, and that means they're giving off X-rays. So they'll look really different in the X-ray than what they might look at in the visible or in the infrared, slightly longer wavelengths than the visible. And so what we've got here is an example of that. The Crab Nebula, a supernova remnant, also known as SN 1054, I'm pretty sure. Yeah, 1054. The earliest recorded documentation of observation of this object was in 1054 by Chinese and Japanese astronomers. That's why it's called supernova 1054. So it was a supernova in 1054. It was bright enough to be visible during the day at that time. And this is the remnant we can see now. In fact, not too long ago, I saw a really beautiful video just showing that over the last 30 years, you can actually see it has expanded a very small amount, even just in 30 years. So this is a very large structure, a very far away from us, that's expanding at a rate such that even over 30 to 50 years, we can actually start to see it expand. But the purpose of this image here is to show that when we look at this object in different wavelengths, we can see different structures. Now, X-rays, which I've got in the top left here, X-rays top left, has been assigned the purple color. Keep in mind, it's a wavelength that our eyes don't see, so it isn't a purple color. We've just had to take images, measure the intensity of the X-rays, and then assign a color to it. And in this case, it's been assigned purple. And then we go up in energy to the ultraviolet. That's the blue image in the middle at the top. Then to the optical, we've called it visible there, in the green. And you can see the structure in the green is quite different to what it was in the X-ray. And then we go to the infrared, the radio, which again is quite different. And then we've got a combined view. So this sort of work, looking at the same object in different wavelengths, is spatially resolving the object. So looking at its structure and seeing how it looks different in different wavelengths and what that tells us about how it is being formed, how it's changing over time. So that's one reason why we want to be able to go to space, to see these different wavelengths. Then I was going to show the picture of my cat, which is essentially from this infrared camera down here. You can grab it at the end of Shashir's talk and have a play with it if you want. There's a couple of things I want to say about this. Just to prove to you that it was taking an infrared image and not just a visual image where it had changed the colors, I've got this thing in the top right. What you can sort of slightly see in my fingers is a bit of plastic. That bit of plastic, I've got it over here as well so you can try it yourself, is transparent in the visible light. So I can see right through it, but the camera can't see through it because the thermal infrared light that is coming from the cat can't penetrate through this, this plastic. So that's why in the top right image, you can see half of the cat, but you can't see the right-hand side because I've got a little piece of plastic covering half of the lens and the thermal infrared light can't go through there. So it's not just seeing visible light, it's actually seeing light of a different wavelength. I'll talk a little bit about radiated light, the heat we're giving off in the form of photons a bit later, because it's really important for thermal control of spacecraft. Because when we want to cool down, we just interact with the air around us, but you can't do that when you're in space. I'll talk about that a bit later. But what you can see here is that a cat's nose is a little bit cooler, or at least my cat Mephisto's nose was a little bit cooler at the time, and otherwise that they were a lot hotter than the cushion they were sitting on. Probably because you can see at the top right of that couch there, he likes tearing it apart instead of using the cat scratchers that we have. He does use the cat scratchers, but why not tear apart a couch when you can? That's what he seems to think. Okay, so I'll catch up with my other one here. Now that we know about the wavelengths we might want to view, and we know why we want to go to space to do that, what we need to know is how telescopes work. But what I'm hoping to show you is that telescopes themselves aren't, at least the principles behind them aren't that complex. They kind of work on the principles of a couple of pieces of equipment I've got down here that I'm going to talk about: gratings and prisms and lenses. The thing that makes it really hard is getting there and engineering them so perfectly so that they still work well when they get there. There's a few other things that make it hard getting to space, but the actual principles of the control of light and observing objects at different wavelengths is not that complex. So first, I'm going to talk about how telescopes work, and then I'll try and talk to you a bit about the instrumentation we use, the different types of imaging that we want to take. So how telescopes work via lenses or mirrors. I was going to have a lens telescope here, but I've just got a mirror one here. And the reason is because I'm going to use it as a bit of example. You can have a look at this telescope. It's a very simple one. We have a lot of more complex telescopes, but they actually can't be easily manhandled like this one can. So it's good to have this one around as well. This is a simple Dobsonian telescope. So what I'm going to talk about first is lenses, because that's the image I've got up here. This is the NASA Transiting Exoplanet Survey satellite camera. It is a camera very similar, if a little bit more expensive and complex, to your DSLR camera. It essentially has a sensor at the back and a series of lenses that are making an image. This particular type of camera was quite a wide field camera, a little bit like your fisheye, though not quite that wide angle. But otherwise, it worked very similarly. So direct imaging, or rather just imaging of objects, involves a camera, and it can be as simple as a set of lenses and a sensor. And in the case of TESS, it absolutely was. There were several sensors, but it was a relatively simple design. But I'll use Hubble as a bit of an example, something sort of similar to this. You can also use mirrors instead of lenses. There's actually a benefit to using mirrors instead of lenses, just like I'll talk about in a demonstration with this prism in a little bit. When light travels through glass, different wavelengths of light bend a little bit different. We call that refraction. In fact, just when I was walking over here a little bit earlier, I could see a rainbow. That's refraction of the light from the sun going through the drops in the air, the drops of water, and water, just like glass, has a different refractive index. When the light enters into the water, it gets bent, separated in the colors, bounces around, and then gets emitted out in a sort of consistent direction because the light's coming from a consistent direction and forms a rainbow. That's refraction, but and that's how our lenses work. But when we use mirrors, we don't have that bending of light. So if we have light hitting a mirror, it's going to reflect off at whatever the angle of the mirror is. When I say we don't have that bending of light, we don't have that wavelength dependent bending of light. All the different wavelengths, no matter what they are, will behave the same when they reflect off the surface, as long as they're not a particular type of light that penetrates through that type of material, like X-rays and gamma rays like to penetrate through just about everything. So we often build telescopes out of mirrors. There's another fairly obvious advantage. If I'm going to mount a lens, like one of these ones I've got here, I have to hold it by the edge because the light has to come in one side and come out the other side. So I've got to hold it by the edge. If this gets really, really big, that gets really hard to hold in such a way that I can now send it to space or move it around, things like that. If I've got a mirror, this one has a mirror at the back of it, just there being held, I can hold the whole one side of the mirror. And that means that I can make this mirror a lot larger. Now, the mirror can still shape the light. We call that beam shaping. And essentially, that's what we're doing with the mirror. We have a curved surface, a bit different from the mirrors you're used to at home. It's curved, and essentially that allows us to bend the light. You can see here the light path. The light's coming in from the right-hand side. It's hitting the what we call the primary mirror at the back there. Where did I put my little laser pointer here? Hitting the primary mirror back here, bouncing off the curve of the primary mirror directs the light to the secondary mirror. This telescope is actually exactly the same. We have a primary mirror, slightly curved, and just up the top here, I don't know whether it's very easy for you all to see, there's a little mounted secondary mirror here. So this light is hitting the curved surface, it's coming down the mirror, down the tube, hitting the mirror, and hitting the secondary mirror here, which is actually at a 45-degree angle, ejecting the light out or directing the light out to this eyepiece just here. That's how this particular telescope works. Now, there are lots of different arrangements of mirrors that we can use to get a good image. And something like this uses a very simple parabolic mirror. It's called a Dobsonian, using a Newtonian style of set of mirrors, whereas the Hubble used different sorts of mirrors, a lot more complex. But the really nice thing about having a mirror-only system like Hubble did is it can work at any wavelength. Whereas once we introduce our lenses like TESS did, it can only work over a limited wavelength range. So Hubble is able to do UV, infrared, all of those sort of different wavelengths really well. I'll talk a bit later about Hubble specifically, but there was one extra benefit of lenses I see that I didn't mention, which is lenses can be made into really complex shapes. We now have the ability to grind lenses into all sorts of really complex shapes. We can do that with mirrors as well, but lenses have that sort of benefit such that we can actually do a bit more with lenses. I know Jonty, who gave me the introduction before, has seen the benefit of some of the next generation of lenses in the Fresnel lens that you've got, where we're now able to grind our lenses to such precision we can lighten the load of our lenses and still do fantastic imaging. Okay. So now we know how our telescope works. We know, for example, if we wanted to build a UV or X-ray observing telescope, we might want to use mirrors, and we can build that structure and send it into space. But what is it that's difficult about space? I asked AI to give me an image of a satellite that's having electrical problems and breaking down, and that's what it generated for me. I'm a bit disturbed at how much it looks like Hubble, actually, but that's fine. We still observe with Hubble and apply to get time on Hubble, so I don't want to see it breaking down. But what's difficult about this? Well, one of the things is we have to send things up into space on rockets, and rockets work by heating up material and throwing it out behind it at high speeds. So that's how things get pushed up, is by pushing stuff down really, really fast. That is a very rough ride that the objects get. That means we have to build them really robust, and we have to test them. And then when they get tested, sometimes they break and we have to rebuild them, all sorts of things. It's quite difficult to build an instrument that's going to survive getting there. And so we have to spend a lot of time planning, building, testing, and making sure that our object's actually going to get there when we do send up something up in space. But also we're under this extreme limitation of we want to keep it lightweight and we want to keep it small because it costs a lot of money to send things into space. The other thing, something that people sometimes don't know about is they sort of say, well, you know, here's a camera over here. This is a little camera we've got. I use it on some of our telescopes. I could just send that into space. That's ready to go. It works well. But actually, whilst I could, and it would work in space for a little while, it won't last that long. Most electronics use a solder type. I think it's the lead in the solder that will degrade over time in space. So in space, not time and space, but in time, in space. And that's because of the way the vacuum works. A lot of things we call sort of outgassing and things like that. Materials release gases and things over time and space, and then they degrade and stop working. So electronics that we use here on the ground that aren't made for space typically won't last more than a few weeks to months in space, depending on the situation. Sometimes we do send things up there, and certainly it's true, we do use connections that you'd be familiar with, USB, you know, Ethernet, stuff like that. There's definitely connections like that still used in space, but we can't usually just take a device from the Earth and send it up into space and expect it to work for very long. What else? Temperature control. So I mentioned this earlier with the thermal infrared camera. Everyone's giving off radiation right now. When you're in space, you're surrounded by a vacuum. That means you can't lose heat very easily. And when you're in space and moving around, you're going to go into the sunlight probably at some point, and therefore you're going to be receiving a lot of sunlight, a lot more sunlight and a lot of energy more than we get when we're here on Earth, because we have the atmosphere to protect us. And that means that a lot of instrumentation, I was a little bit surprised to learn this just a couple of years ago, that we send into low Earth orbit often is at around about 0 to 80 degrees Celsius that we're normally thinking, that we're normally living in. And that's because even though space is thought to be very cold, things heat up when they get in the sun and they can't lose that heat very quickly. And that's because when we want to lose heat, we go to a fan. We go to something that blows colder air on us. When you're in space, you don't have that ability to exchange heat with other molecules because there are no molecules around you, so you have to just radiate your heat away. So when you receive heat, you need to make sure that you can radiate it away. And when we're building an instrument, we need to think very carefully about how we're using our electronics, because our electronics heat up. My computer over there is pretty hot right now because it always runs very hot. That is not a good device to have in space because it's going to have to run a lot hotter. So we have to be careful with the electronics that we take into space, because those electronics will heat up, they'll create heat, and we won't be able to get rid of that heat very easily. So we're generally working with very limited amounts of power. And of course, solar radiation. Solar radiation isn't just the light. There's also particles, charged particles. In certain parts of the orbits around the Earth, there are a lot of charged particles that can cause a lot of trouble for electrical equipment. So there's lots of challenges with electrical equipment in space. And then last here, we have control systems and recovery. It seems fairly obvious, but it can quite easily get forgotten that once you've sent something into space, you can't do a lot about it. So you really hope you've designed your control system so that it can reboot nicely, so that it can, fix itself when it has a problem. And it's very regular, particularly when missions are just starting out, to lose control of a satellite and for it to potentially either destroy itself or just not be able to open up its solar panels, like you can see in this image here with the solar panels out, and therefore not be able to get power and not be able to ever function correctly. I mentioned Hubble a little bit before, and I'll mention it a bit more later. Hubble is an example of a satellite that went up and almost immediately needed to be fixed because there was a problem that had been built into the design of it that needed a servicing mission. Luckily, Hubble was planned to have several servicing missions, and it's had 5 now over the last 30 years or so. But almost immediately when we sent Hubble up, we did have to do a service. But that is not typical of most space instrumentation. And so as I was talking about thermal, I was supposed to flick onto this page here. A lot of large satellites have big protective covering to protect themselves from the light. JWST is working in the infrared. That includes getting close to thermal infrared wavelengths. And so since it's working in those infrared wavelengths, it needs the equipment that's sensing those wavelengths to remain cool. So it has to block the light from the sun very well. So it has a really big protective sail there, protecting its instrumentation from the sun. So it orients itself in its orbit to protect its equipment from the sun. So now we have lots of information about how to build a piece of equipment. Are we ready to build an instrument? Well, we could start getting onto the optical design, but as soon as you start going to optical design, one of the first questions you ask yourself is, what's the resolution of the instrument that I like? And the reality is we can't get everything we want. We can't get something that's got fantastic resolution, can see over huge ranges, and can see down to really faint objects without requiring our spacecraft to be gigantic, to be away from the Earth so we don't get any Earth shine, to be probably something that's not really feasible. So we still have a few more questions to ask. And most of those questions boil down to, what are we trying to do? What wavelengths do we want to look at? Are we in a situation where we can go to a really big telescope so we get really good angular resolution? That will be expensive, very large, very heavy. So we have to ask ourselves, what are we trying to do? What are we trying to investigate when we go to design an instrument? So it's usually one of these four sort of things. Most of the science we're doing, and again, I'm science driven, not military or Earth observation or things like that, but astronomy in particular, astronomy science driven, then we're asking ourselves, are we trying to spatially resolved objects? Like I said before, this is a multi-wavelength view of the Crab Nebula, and it's interesting to us because we can resolve that as an object and see its structure in different wavelengths. So do we want multiple wavelengths? Do we want to resolve it? Or do we want to make brightness measurements over time? This is a little plot of a supernova. You're going to see a little dot in the left-hand side of that black strip across this galaxy, glow bright for a short period, and then it's going to decrease in its brightness. This is time-resolved brightness measurements. Over time, this object got suddenly bright and then dimmed. This is a sign of a supernova. So you can see that object, it stayed bright at the end there, just there, get bright, and then go fainter over time. You might want to observe an object and see how its brightness changes over time over a particular wavelength. And there are lots of reasons to do that. In this case, it's for detecting a supernova, understanding what type of supernova it is, and supernova have all sorts of interesting characteristics that allow us to measure some of the longest distances in the universe, or it might be to find an exoplanet. A lot of us here do work on exoplanetary science, so I do have a little bit of a focus on that in any of my talks. This is an example where, although they're showing a star as if it is a resolved image, realistically, almost all stars other than the sun are not resolved at all. They're just a point source and an incredibly long distance away. So we can't resolve them like you're seeing here, but what we can do is measure their brightness, which is this line that's sort of being shown here, time going to the right, increasing to the right, and then the brightness here on the left. We can see an object dip slightly in brightness and then increase if it has an exoplanet orbiting around it that happens to have an orbital alignment so that the planet passes across the face of the star. Just like Venus does occasionally from our perspective here on Earth. We're looking at many, many millions of stars in the sky. Occasionally, there will be a planet orbiting around one of those stars where its alignment of its orbit is such that it passes across the face of the star. Roughly speaking, the chances of that for any given planet are about 1%. That it has that kind of orbital alignment, and that means we can potentially detect the dip in brightness of the star as the planet passes across the face of it, and then be able to detect the size of that planet relative to the size of the star. So brightness measurements over time, that's something we might be interested in trying to do. Location information, that doesn't sound like a very interesting topic, but Gaia has been doing an amazing job over the last few years. I'm going to talk about Gaia a bit later in more detail, but it's been doing an amazing job of trying to understand the motion of stars. Some stars are really, really far away. That means even if they're moving really fast, we're not going to see them as moving on the sky. Some stars are closer, and so that even over a few years, we won't really see any motion unless we're looking really closely. But Gaia has an amazing resolution, and so it's able to measure the positions of stars relative to other stars incredibly well, and it can see the motion of stars that are closer to us. And that actually allows us to determine how far away they are. And knowing the distance to stars is a really fundamental thing we need to know about stars so we can understand their sizes, their brightnesses, and what that means about their evolutionary state. So we may want to know about location information. This is another example of location information that was done by TESS. TESS, the Transiting Exoplanet Survey satellite, was actually out there trying to do that exoplanetary time series brightness measurement that I was talking about before. But just when it started its scientific commissioning, it caught a comet in the very nearby and very bright, as you can see, moving across the sky. The black and white dots are actually stars. They're trying to use a technique called difference imaging, where they decrease the apparent brightness of the stars by subtracting the average brightness of the star from the whole image. And what you can see, because the comet is moving so much, it still shows up even though the stars are much less bright than they would have been without this difference imaging technique. So understanding the positions of various things, whether they're local phenomena within our solar system or whether they are stars out there in the entire galaxy. But then the other thing that you might want to know about an object is you might want to do spectroscopy. You might want to know about its brightness as a function of its colors. That's mostly what I do. So I'm going to do a brief diversion for a couple of slides on spectroscopy. Spectroscopy in this image, what it's trying to do is say, okay, here we have some kind of, what is it, Eta Carina? Jonty might remember what that's. What's cataclysmic variable or something?
Down near the end of its life, that back in the 1800s, was briefly the second brightest star in the sky. And at that time, it shed a huge burst of mass.
That's right.
Several solar masses. And that's
yeah, that's right. So right near their end of their life, the stars tend to blow off an outer layer of gas. And because inside they are very bright, the leftover material, the star on the core, is giving off lots of radiation. It illuminates the material that it's blown off. But what we are showing here is there's a little slit just down the middle of that image, and out of that slit, they've got this sort of beam coming out. What they're trying to say is, as you're seeing the changes of color, this is a STIS image, that's a spectrograph on Hubble that is looking at UV light, although they've drawn it as sort of green and red, that's in the UV. And you're able to see different atoms that are showing particular bright peaks. That means those atoms are actually in that slit that is in that variable star, that bright flash that's come off Eta Carina. Why are those materials there? How does that work? That's all the side of the theorist. I'm mostly an observer. I couldn't tell you particularly why those metals are present in an exploding variable like that, but you get that information from getting the spectrum of the object that you're looking at. Now, here's an example of a particular type of spectrum. If you do, so down here, we've got an example of a very simple spectrograph, simple situation where we have a white light source, an LED, that's giving off light of almost all colors, and then a little system that goes to a grating. I'm going to talk about gratings very soon. And then we get a spectrum here of the white light that we're emitting. So we're breaking the light up into its different colors. You can see there's just a little gap there between sort of blue and green where it's a bit fainter. LEDs actually don't emit quite smooth spectrum. There's a little bit of a color, sort of a cyan color between blue and green that LEDs don't really emit too much light in. But if you build a spectrograph in a particular way using a particular grating, rather than just getting one line of light like this, we can get a folded line of light like this. This is what we call an Echelle spectrograph. And in this situation, we can see the light. This is a solar spectrum, so it's the light from the sun of all the different colors that it's emitting. And it has lots of black dots in it. Those black dots are absorption features. So coming out from the core of the sun, in the core of the sun, we have nuclear fusion. We have really high energy photons, which are bouncing around inside the sun. But that is a continuous spectrum of light when it comes out the outer layers of the sun, except there are a few particular wavelengths at the outer layers of the sun that will actually absorb light, and that's those black dots there. Those few particular wavelengths are from atoms in the outer layers of the sun. And the outer layers of the sun were at about 5,800 Kelvin. In the core of the sun, we're at billions of Kelvin, or billions of degrees Celsius, if you like. At 5,800 Kelvin, we can still have atoms. Atoms kind of like where we've got all around us right now. They're at a different temperature, so they're moving very fast, but they're atoms. They've got a nucleus and they've got electrons bound to them. Unlike in the very core of the star where we have nuclear fusion going on, in that situation, they aren't atoms. It's a plasma of nuclear cores and electrons. So there aren't atoms in the very hot core of the sun, but by the time we get to the outer layers, there are. And those outer layers, those electrons bound around the cores, they can absorb very specific wavelengths. They absorb them, and the electrons change their energy level in an atom. And they have particular wavelengths they'll absorb at, and that's what we're seeing, those little black lines. They're kind of like a fingerprint or a DNA of the sun. They tell us the types of material that are in the surface of the sun. So there's lots of benefit to splitting that light up. Rather than just getting an image of the star, we split the light up into the spectrum and we can tell all sorts of information. One of the things we can tell that I spend a lot of my time doing with this particular type of high resolution spectrum you get from an shell is the speed of the star. We can get the radial velocity. We get this from the Doppler method. The Doppler method is very similar to what you experience when a motorcycle or a truck is coming towards you. When it moves towards you, you hear it as a higher pitch or a higher frequency. When it moves past you, it sounds sort of goes, meow. It sounds like it's a lower frequency. That's the Doppler effect. When it's moving towards you, it's compressing those sound waves. So they sound like they're a higher frequency or a shorter wavelength of sound. When they move past you, it's stretching those out because it's still emitting the same sound, but it's moving away from you. So it sounds like they're stretched out. That's the Doppler effect. The same sort of thing can happen with light. The difference is that motorbike was probably going about 1/20th or 1/30th of the speed of sound. And the stars, well, we can measure the speed of a star down to about 1 meter per second, about the speed of me walking slowly. But the light is traveling at 300,000 kilometers a second or 3 million meters per second. So the fraction of change of the wavelength of light due to the motion of the star is very, very tiny, which means it's a really, really difficult measurement to make. But with spectroscopy, we can measure the speed of stars as well. I didn't want to go into too much detail there. I'll try and stop. To give you a little bit of a demo of what you can do with the equipment I have right here, as well as this little spectrograph I have an example of, I have two things, a grating and a prism. These are the two ways we split up light. You might think it's a really, really complex thing, splitting up light to get those spectra you're just seeing, but it actually works via very simple principles. Refraction, which I talked about a little bit before, that you can do with the prism. That is what I'm doing here. I'm holding this prism up. It has one side that's misted, so when you go to use it, don't look through the misted side. But essentially, if I want to look over there, if I hold this prism up here and look through that way, I can see things like the lights over there. And what's happening is because those lights have white light in them made up of different colors, those different colors are getting split just a little bit. You can see the light in my office or the room just outside my office getting split into its blue and white in the middle where it should be green. That's where the actual light is, and then red on the other side. The light is being split, its colors up. So that is refraction, and that is one of the main ways we use to split light up. The other is diffraction. That's what this diffraction grating does. And this is looking through the diffraction grating at the same light. The diffraction grating works on a different principle. That's why it's called a different name, diffraction instead of refraction, which I'll just talk about briefly because spectroscopy is such a big thing for me. I couldn't let you away with just showing it to you. I had to tell you a bit more about how it works. So real waves, just like ocean waves, water waves, they go around corners. When they go through a gap, like in the top left here, they don't, even if they're coming in flat, and you can sort of see the waves in the left-hand image are coming in flat from the sort of bottom right-hand corner. When they hit the gap, they go around the corners. Okay, this is the way in which light travels. Remember, light is a wave. It's also a particle, but it can behave like a wave. When light goes through a gap, it goes around corners. So if we have a grating, that thing that I was showing you, what it does is have lots of little gaps and lots of little blocking parts. That means when light travels through those little gaps, it goes around those corners. So you get those sort of rings coming out of every little groove in my grating. So on the left-hand side there, you've got these round waves. The lines there are supposed to indicate a peak of the wavelength. So remember, the wavelength is sort of like that. You've got a peak here, that's a line, another peak here, another peak there. So as the line is propagating from the left, sorry, the wave is propagating from the left to the right, it's going through those little gaps and propagating, going round the corners. And then you get this sort of interference pattern. Now, there's only 2 grooves here, but in a grating, there's thousands of them. But what really matters is you get this interference pattern that means that because the light's gone around the corner, light coming from one groove travels a little bit further, the distance denoted by delta S in this little figure here, travels a little bit further to go in one direction than it does to the groove next to it. So that means all of the light going off at one particular angle, every groove has traveled a little bit of a different distance. That means at some particular angles, these waves will interfere constructively. One wavelength that's going like this will happen to line up with another wavelength that's traveled a bit further, but its wave is also in exactly the same state. That means we get this addition of those wavelengths, and that shows up as a brightness at that particular wavelength. But because all of them have different wavelengths, what we get out of it is a spectrum. And I think I was supposed to have a picture of this spectrum right here, but I guess I've got it in front of me. And what you get out of that is a spectrum. When you come off a grating, this is exactly the same as this grating I showed you an image of looking through before, but it's a reflection one. You can do it reflecting, or you can do it via transmission, the light going through it. This is a little diffraction grating, so we've got light focused onto it, and it's getting diffracted at a particular angle, and you can see at different angles, the different spectrum, the different colors will add up. And so you'll see blue here and red over here, where you get this coherence of the light, and that interference pattern adds up for different wavelengths. So now we know pretty much everything we need to know to build an instrument. We just need to know what we particularly want to study, and therefore we would know how to build an instrument for the most part. Now, there are an incredible number of space telescopes, far too many for me to cover. In fact, I've probably already talked for quite a while. I have, indeed. I don't have all of these, the time to talk about all of these, but most of our work here at UniSQ does have a strong exoplanetary focus. Up in the top left, you'll see a few names like Hubble, TESS, JWST, and I had a couple of minutes set aside to talk about some of the major discoveries that have come out of those telescopes before I wrapped up. The NASA fleet is huge, tremendous number of objects, but Hubble is one of their flagship missions. Hubble was, like I said earlier, an instrument that was designed to be able to do lots of different things, and it has done an incredible number of things in its lifetime. It was launched in 1990, 5 servicing missions, as I said earlier. It's still operating. We still apply for competitive time on Hubble to do things studying exoplanet atmospheres. They still use it to do deep field images. It is fair to say that JWST, James Webb Space Telescope, that I launched only a couple of years ago that I'm going to talk about soon, is better at most of that stuff than Hubble is, but it's a brand new telescope and costs many times more than Hubble did. Hubble is still an incredibly useful instrument. It has a 2.4 meter primary mirror. So what that means is, one of the things I sort of didn't get around to mentioning when I was talking about instrumentation before, is if we want higher resolution, angular resolution, we want to be able to resolve smaller structures further away, then we need a bigger diameter primary mirror. And so Hubble's 2.4 meter primary mirror, that's a pretty big telescope. James Webb is a lot bigger, but it's still a really big telescope. It's had many instruments, including infrared cameras and UV spectroscopy. I showed you a couple of images relating to that. But some of its major discoveries, it had an incredible deep field image that enabled it to determine the rate of the universe's expansion. That the Hubble constant is what we usually call it, although it is true that we've found over the last 20 years that the universe is probably accelerating rather than expanding at a constant rate. Early galactic structure, which I'll talk about a bit more with JWST soon, and evidence of black holes in the centers of galaxies. Something we now know as of very recently is also true in some globular clusters. Those are clusters of stars within galaxies, or those black holes aren't quite as big as the supermassive black holes, billions of stellar masses in the center of galaxies. And of course, it also did some fantastic exoplanet work. Kepler, the Kepler space mission launched in 2009 was revolutionary for exoplanets. I could probably talk for an hour on Kepler alone, but the main thing I'll say is that its task was to understand the population of exoplanets out there. It stared at one part of the sky that was about 16 times the size of the moon for 4 years, taking measurements of the brightness of stars with that image field right there every few seconds. There's an example of that detector, very special detector, curved surface, amazingly large compared to the little detector like I've got. You'll be able to see that one at the end, the detector in there. It was an amazing achievement at its time, and it did an incredible job. Kepler performed fantastically. Unfortunately, one of the things we found out, we were trying to find how many Earths there are out there. So we were trying to use this transit technique, which I've already discussed with you, to find planets orbiting around those stars in that star field that Kepler was looking at. Before Kepler, we knew about quite a few planets orbiting around other stars. We call them exoplanets. This was in 2009. We knew about Jupiter-sized planets that were orbiting around stars in fairly long period orbits. You can see down the bottom here, bottom right of this figure on the right, the orbital period ranges from just a few days. That means the planet is orbiting around its star in just a few days. It's an incredibly short orbit. Keeping in mind the shortest period orbit we've got is around 50 days for Mercury in our solar system. There are many planets out there that orbit around their host star in just a few days. But we knew about lots of Jupiter-sized planets, but very few smaller planets. But after Kepler, we knew about thousands of planets, 4,000 or so planets came out of the Kepler mission. Many of them much, much smaller, all the way down to, as you can see, Earth mass sized and smaller. There is a little bit of a transformation there on the first image. We're going from mass on the y-axis, and here we're going to radius, but we can make a sort of a relationship that allows us to do that. And what we see is that what we learned from Kepler, one of the major things was that even though prior to Kepler, we knew about a lot of giant planets, Jupiter-like planets, and not a lot of small planets, when Kepler came along, it proved to us actually there are far, far more smaller planets than there are bigger planets. So probability on the left-hand side of this plot on the right is logarithmic. We're going from 1,000th in the lowest number on the left-hand side axis up to 0.1, 10% chance on at the top. So it's a logarithmic change of probability. And what we're doing along the x-axis is showing the increasing radius planet size. So you can see smaller planets, those with radii from about 1 Earth size up to about 4 Earth size. That's like the size of Neptune, one of the smallest gas giants in our solar system, are much more likely to be found around other stars than those giant planets. So that's what Kepler told us, and that was an amazing revelation. K2, I won't talk too much about K2, and I wasn't going to talk about TESS, which is why I've blurted out there, because I know Shashir is going to talk about TESS in his talk. I had a couple of slides there. Gaia, I mentioned earlier, and I think I've only got one slide about Gaia, but Gaia is doing an amazing job measuring the positions incredibly precisely of about 1 billion stars a few times per year, measuring the brightness of those same stars and measuring the spectra of those stars. That means we not only know the position on sky of these stars and how they're moving relative to us on sky, but also we know how their radial velocity is, because we get that Doppler information from that spectra, like I told you a little bit about before. So Gaia has revolutionized the study of stars, the galaxy, and galactic structure. JWST, I couldn't pass by without, I couldn't talk about any space instrumentation without talking about it. It's got lots of instruments, which I don't have time to talk about. For example, this is an incredibly competitive instrument, but NASA works fantastically in that it makes all of its amazing instrumentation open to anyone to apply. So I was reading a proposal from some of our team here, and I'll probably be reading another one tonight. I was reading one last night because JWST's proposals are due in just a few days, the 16th of October. So we can all apply for time on these instruments, even though this was a $13 billion instrument built over 20 years by NASA. And it has a number of different instruments designed primarily to look in the infrared, which is why the names are all MIRI, NIRCam, NIRIS, and NIRSPEC. NIR stands for near infrared. MIR stands for mid infrared. We do have a fantastic naming system. But one of the most amazing things to come out of this instrument was another deep field image. So I'll just quickly point out that with a deep field image like you have on your left-hand side here, you've got a whole bunch of blurry objects, and then you've got a few that have this sort of shape like that. Those are the stars. Every other object you can see is actually a resolved galaxy that allows us to study many of the other galaxies that are visible to us. We can understand their structure, what type of galaxy they are. We can usually determine how far away they are. JWST has been able to look back to the very earliest stages of the universe, which I'll talk about just after I talk about this, which is the main thing that we apply for time here at UniSQ for time on JWST is to look at exoplanet atmospheres. JWST is the first time we've been able to study in great detail the atmosphere of an exoplanet. When it's transiting, when it's passing across the face of the star, some of its atmosphere is also blocking out light. Now, I'm going to skip this video because I've got a better one coming up that'll tell us about it. This is the kind of information we can get from an atmosphere of an exoplanet. That is, we can see sodium, water, carbon monoxide, carbon dioxide, even sulfur dioxide present in the atmosphere of the exoplanet. And we can do that because, like I was saying, this is a video here, which is a little bit better. When a planet is passing across the face of the star, some wavelengths will correspond to the absorption of a particular molecule, like water. Water absorbs at 1.4 microns, for example, although that's not one of the ones we've got here. So that means the planet, if it's got water in its atmosphere, will appear a little bit larger, will block a little bit more light at 1.4 microns because it's got water, and water absorbs at 1.4 microns. But at, say, 1.5 microns, there's no longer the water absorbing at that wavelength, and therefore the planet will appear a little bit smaller. So what we measure, going back to that image I had before, is the size on the y-axis, the size the planet appears when it's blocking out the light from the star, versus the wavelength. And we know the different wavelengths correspond to different molecules in the atmosphere. That means we can start to look at the chemistry occurring in the atmospheres of these planets orbiting around other stars. Now, for the most part at the moment, these planets are Neptune-sized or bigger, so gas giants, not exactly the terrestrial planets we want to be able to study the atmospheres of. But this is the first time we've been able to do this with this kind of detail. It's been an incredible breakthrough for us in the last couple of years. And I think once we've got a really good hang of what we can learn from JWST, the next generation of telescope that's capable of this may well be able to look at Earth-sized planets, terrestrial planets, and their atmospheres. JWST will try, but for now it's doing what it can with the larger planets. And the early universe stuff that it's found out has been amazing. I know Rebecca will probably talk about the cosmological understanding that we've come about through JWST over the last couple of years. So even though I was going to talk about it now, I know I'm running over time. So I'll leave it for now. This was going to be my last slide, so I think I'll play it. It's just a very short video showing the light path of NIRSPEC. NIRSPEC is that instrument that gave us that fantastic spectrum of an atmosphere of an exoplanet. I wanted to show you this because I think it demonstrates how the instrument is made up of lots of different parts, but those parts aren't complex. Most of them are mirrors. What's going on there is the light is just being bounced around from flat mirror surface. Then it hits some mirrors that are not flat. These mirrors that it's bouncing around in are not flat surfaces, so they're beam shaping, just like the curved mirrors here. We're doing a lot of beam shaping to get the image the right size. When it goes through those little circles there, those are filters. I've got some examples of those here where we have a filter that lets through green light but blocks most of the other colors, and a filter that lets through infrared light. It looks like it's completely opaque to us. That's what that's designed for. And then you see the light bounce around until it eventually hits, there's some more curved surfaced mirrors, eventually hits a grating. That grating splits the light up into its different colors, and then it goes into the camera and starts reading out ones and zeros, which it's about to do now. Now, you might ask, why are there so many mirrors in this thing? And that's where the whole space saving comes in. Sometimes we need the light to travel a long distance, but there's no long distance to have. So we just bounce it around a whole lot and have flat mirrors and have those mirrors really well cleaned and things, so most of the light bounces around so that that light can spend its time spreading out. So we have a lot of mirrors, but the actual principles of some of the most complex instruments we have in space, like NIRSpec, all come down to gratings, prisms, and filters. So I think I'll probably leave it there, but thank you very much for your attention. I'm going to hand over
and take some questions. I think we'll allow 10 minutes for questions, and we'll split that for some questions from online as well. But we'll start with questions in the room. So if anybody's got any questions in the room, please raise your hand and we'll get a microphone to you as quickly as we can. Got a question right at the front, and family privilege, I'll give my mum the microphone.
Well, I'm interested to know what anybody would think, given the vastness of the universe, about the possibility of extraterrestrial life. Not necessarily humankind, but maybe different sort of form.
That is a really great question. I'll just flick back to this image, because this image shows thousands of galaxies in one tiny patch of the sky. Every one of those galaxies has billions of stars in it. Our own galaxy has of the vicinity of 300 to 500 billion stars. I didn't get much of an opportunity to speak about it with regard to Kepler, but Kepler told us that we have on average about one planet per star. So we have some stars with a whole system of many planets similar to our own, and we'll have some stars with no planets. But there are billions of planets in our own galaxy, the Milky Way, and so there are hundreds of billions, if not trillions, of galaxies out there. So I think that life in the universe is almost definite. Whether we can actually interact with it is a different question. If you take, for example, the age of the universe, it's around about 13.7 billion years. People have argued that we could get to the nearest stars, the very nearest, in a few hundred years. So let's imagine we were organized enough to get together on a rocket and we decided to go to a nearest star system, and we were willing to commit to multiple lives living on rockets to get to a star system where we could try and settle down and have life. We found a planet, we knew it was there, and we went and lived on it. At that sort of timescale, over 1 billion years, we could populate most of the universe most of the galaxy, not the universe, most of the galaxy in 1 billion years. Now, the universe is about 13.7 billion years. You might argue, why isn't the galaxy already populated? And this is a good question. This is something we don't necessarily know the answer to, but there are lots of really good talks from astronomers and other people, philosophers and so on, about why that might be the case. But that's why there is a very legitimate scientific search for life in our galaxy, because there may be life in our galaxy. But it is fair to say that as far as we have seen scientifically, we don't see any direct evidence of life at this stage, although that's debatable also when we talk about Venuses and things like that. There are certain places we're still looking within our own solar system for the possibilities of life. But complex life like our own, is it out there? I certainly think it's incredibly likely given the scale of the universe, even if the probability of the development of complex life is incredibly small. There's so many trillions of opportunities for it that it is likely. But there's a lot we don't know. We can't create life in a lab. We don't know how to actually make life from constituent parts. So there's a lot for us to understand fundamentally before we could say, yes, there's likely to be life there, or no, there isn't. So at the moment, we're looking for the signs of life. We haven't found any, shall we say, definitive proof yet, but there are some possibilities that we're still looking into. It's a good question.
It's pretty common knowledge that dust is a big issue in mechanical systems. How are they stopping dust from getting on the mirrors of Hubble or James Webb?
So dust is a problem when you're building it here on Earth, a massive problem. We have clean rooms, clean boxes, often clean boxes in clean rooms to try and keep everything as perfect as possible. Once it goes into space, we do have problems with particles irradiating it from the sun and even impacts from micrometeoroids. In fact, JWST, not too long after it was launched, one of its mirrors went slightly out of alignment because it received an impact. And that impact, JWST is an incredible piece of machinery. It had to unfold itself into its correct shape when it got there. And the alignment of its mirrors is incredibly precise. So they were able to detect, and even now you can still see the distortion caused by that impact. So there are problems with equipment in space. Dust itself, we don't have too much of, in the sense that once it's in the vacuum of space, there isn't too much dust generally floating around, but particles on the scale of even a tenth of a centimeter are challenging for objects in space because they are moving at kilometers a second. I did have a few slides that I had to remove, talking about how we go up into orbit and propulsion and speeds, but typically everything that's in an orbit starts at about 170 or so kilometers above Earth's surface. That's low Earth orbit. Even at that height, you'll probably only last in orbit a few days before you would interact with the upper parts of the atmosphere and start to experience drag and fall down to the Earth. But a lot of objects are in that 300 kilometers to 500 kilometer zone in low Earth orbit, and they are moving at 10 kilometers a second, 11 kilometers a second. So they're moving incredibly fast. So even small particles that may be on some different trajectory to you can be very damaging. So those are a big problem for us when we're in space. Yeah, I'll be around.
It's less of a question, more of a proposition. What if instead life occurs all the time, but instead doesn't have the genetic information to tell itself to reproduce or to split itself? That instead it's a unique design on Earth.
Yep, that's a really good question. There's so much about life we don't know. Another idea that's very valid is that there are sort of choke points that life may not be able to make it through. For example, I gave a talk quite a few years ago when I was working in Sydney about life potentially being surrounded by garden worlds where we've got life that has developed but never developed into what we think of as animated life or non-plant life. Our own Earth, and Jonty knows a little more about this because habitability is more his area, but our own Earth went through massive changes to its atmosphere when life first formed. We have evidence of it forming first in a very carbon dioxide-rich atmosphere, forming anaerobic bacteria that converted the atmosphere into oxygen. And so there are so many changes that have occurred only on Earth, and it's our only example of the formation of life that there's so much about it we don't know. So it's a very good question. The idea that life could be forming and not surviving is a very valid thing to put forward. Even the idea of how we first formed life from RNA, that's one component of ourselves now. We believe Earth, some of early life may have formed from an RNA world. There's evidence of molecules, the components of life-forming molecules out there in nebulae and things in space, but we don't know how they could have came together to form something as complex as RNA and then formed replicated to form RNA all over the world that then developed into more complex life. There's so much we don't know that we still need to work out. And so that's why, as I said, at least from an astronomy point of view, we're still trying to look for the signs of what we call disequilibrium in our chemistry of the atmospheres, because one thing we do know is life creates disequilibrium in the environment around it. Indeed. So there's so much we don't know there, and Jonty also can have great conversations about those topics.
Yeah, lots of good fun stuff there. So thank you for the questions in the room. Right, so we have 0 questions online. We will hand over to Shashir's talk. We'll move things over. For those who are online, if you want to ask some questions that the speakers can answer towards the end of the talks, please feel free to type them in the Q&A box.
And if I can just add one other thing for those people here, we'll be around after Shashir's talk, and please feel free to play with the equipment up here. It's for hands-on. So yeah, definitely have a look at it.
And I'd like to introduce Shashir, who's working on his PhD with us and has had a very, very exciting year. And I think he's going to tell you all about that, among many other things. So over to you, Shashir.
Thanks, Jonty, for that introduction. Yeah, I'm a graduate researcher at the University of Southern Queensland here. You can probably tell I'm not originally from here, but I've been working on my PhD here. I research all things relating to exoplanets, characterizing them, discovering them, And over the past year, I've been lucky enough to lead a project in discovering a new planet that's pretty exciting. It's called Gliese 12b. And I'm going to talk about that planet today a little bit. And I'm also just going to give you a general context for the field of exoplanets, the different kinds of exoplanets we've seen, some questions about habitability I'll cover a little bit about. And I encourage you all to think about questions that you might have for me, and I'll be happy to answer those. I think my talk will be probably pretty short, so you're welcome to ask questions afterwards. So this is actually an artist's rendition of Gliese 12b, and I'll cover that whole thing in a bit. Cool. So Gliese 12b made a bit of a splash with the media earlier this year. It was covered by BBC, NBC, CNN. I guess this all started with a NASA press release, and kind of a bunch of different media outlets spun it off from there with varying degrees of accuracy. Some from people claiming that it could support human life to people claiming that it's habitable. And I'll kind of cover whether these claims are reasonable or not. Yeah, it was definitely well liked by the media for reasons that I'll get to in a bit. But all of this started with something that looks a little bit like this. So the NASA TESS spacecraft basically took images of this star over time. And from those images of a star field, it was able to extract the brightness of this particular star. It produced a graph of brightness on the y-axis over time on the x-axis, right? And you get something like this. And you probably will not even be able to notice these. There's tiny little blips on this graph. And a year ago, this is something that I was looking at. And like me and a team of other people at the University of Southern Queensland realized that this was actually really, really cool. And I'm going to get into how all of that happened and what our thought process was. But first, I'm going to have to step back and basically give you a bit of a context for all of this. And so for you science fiction enjoyers out there, exoplanets are very commonly depicted in media. You might have seen Tatooine from the Star Wars movies. It's a planet that orbits around 2 suns. So there's a wonderful, wonderful world of exoplanets out there in the media, and Tatooine is one of them. More recently, if you watched the Dune movie or if you read the Dune book, this is like a planet that's like a desert planet with very little water, where water is a very precious resource. So Frank Herbert imagined a planet like this. Then I'm not actually going to play this video, but if you've watched Interstellar before, there's a planet that's orbiting around a black hole. And because of the tides, the extreme tides on this planet that the director, Christopher Nolan, of the movie Interstellar imagined, time actually passes differently due to general relativity. So part of the plot of this movie is how that affects the story that they're telling, where on this planet, some like every minute that passes is like years on the Earth. And this is like another imagination of a kind of exoplanet. So how accurate are these? Are these realistic kinds of planets that we see out there, or are they not? So Kepler, this is actually kind of outdated. I have another slide that shows the correct number. But Duncan already talked about Kepler. Kepler was this incredible spacecraft that was staring at a patch of sky about your hand's area on the sky for its entire lifetime, about 4 years. And it was taking like measurements of the brightness of all of the stars in its star field and trying to detect these transits. The planets crossed in front of the face of their stars, blocked a little bit of their light, and from that, you can infer the presence of an exoplanet. And it was remarkably successful at doing this. The catch was it's pretty small area on the sky. So while it was able to find a lot of planets, it can't do this all over the sky. And so when Kepler ended up reaching the end of its lifetime, another spacecraft was devised called TESS that was supposed to do a similar thing to Kepler, except it has a different strategy. So what TESS does, it's a much smaller telescope than Kepler. And what it makes up for, or what it loses in size, it makes up for in search area. So the idea of TESS is that it takes much larger areas of the sky and it kind of scans the sky in this pattern. So it's designed to try and search the entire sky for exoplanets. What's the idea here? The idea is that We want to be able to search for planets around the brightest stars in the sky, around the most nearby stars in the sky. These are the stars that are characterizable. These are the stars around which, if we find planets, we will be able to understand their characteristics, their conditions, for whether they might be suitable for life, and basically understand them in a lot better detail than we would have been able to with the planets that Kepler found. So TESS was just kind of getting started back when I started doing research in astronomy, and it's been remarkably successful at its goal. It's already found planets all over the sky. So again, what we're using is the transit method. We're looking for these little dips in brightness when planets cross the face of their stars. It's like trying to see a little fly crossing in front of a lighthouse when you're like very, very far away. It's like on the other side of Australia, if there was a lighthouse and there was a little fly crossing in front of it, you're trying to infer the presence of that fly by the dip in brightness as it crosses the face of its host star. So based on the depth of the dip in brightness, that like a deeper dip in brightness would be caused by a larger planet because it would block more light, right? So not only can you figure out the size of the planet, you can also figure out the expected temperature, because a planet that's like much closer to its host star will be orbiting much faster, and therefore it will orbit every, like, say 10 days, right? And that means that it's a lot closer to its host star. A planet that's a lot farther away, something like the Earth, would transit its host star every 365 days. And so you could infer that it's a lot cooler. So the transit method gives you some crucial pieces of information, which is the size of the planet and something about its temperature. And we can get into that in a little bit more detail down the road. This is why the transit method has been so successful. I should note that it's really important for when you see one of these transits, right? It's really important that those transits are like that you observe actually are periodic, because you can say if it transits once and then it transits 10 days later, then you have to expect another transit another 10 days later, right? It's predictive, and we can go out and actually test that prediction. The other method that Duncan touched on briefly, but that I'm going to try and describe as well, is called the radial velocity method. So this is using that Doppler shift. It's splitting up the light of the star into a spectrum and using that spectrum in order to figure out the velocity of the star in your direction, right? And this is kind of like, I like to think of it as if you've seen those radar guns down the highway when you're driving around that measure your car's speed. It's similar to that. We're like pointing these radar guns into space and looking at the speed of stars. And if a star is wobbling due to the influence of an exoplanet that's orbiting around it, right, and kind of tugging on that star, you'll actually detect that little wobble. And that wobble tells you something very important about the planet that's different from the transit method. That wobble tells you the mass of the planet, because gravity works on mass. A more massive planet will result in a larger wobble. So together, you can actually use both of these techniques together. And for those, I think at this point, there's 5,700 plus planets where we have the transit method. And for some subset of those 5,700, we have both the transit method and the radial velocity method that give us both the size of the planet and the mass of the planet. So together, those two numbers give us the density. And the density is a really important number because we can say whether a planet is gaseous, because a gaseous planet would have a really low density. We can say whether a planet is rocky, because a rocky planet would have much higher density. Density tells us something about the composition of these planets. So together, piece by piece, we're kind of building up a picture of what the planet might be like, right? Each method gives us some important information, and we're piecing them together to come up with the characteristics of the planet. So we have even more techniques than this to characterize planets, and I'll cover those in time. But I'm going to capture your imagination for a little bit with some of the planets that have been actually discovered by the Kepler mission and by other telescopes around the world and in space. So Kepler-16b is a particularly cool planet. I think it's particularly exciting because it is a planet that was found around two stars. In fact, it's so similar to the planet Tatooine. This is a fun fact that the Kepler team told me, that they actually brought George Lucas over. They had him give them the naming rights for for the planet Tatooine so that they could nickname the planet Kepler-16b Tatooine. So we actually have a planet called Tatooine, nicknamed Tatooine now. Kepler-186f is another really cool planet that's orbiting around a red dwarf star. And TRAPPIST-1e is another cool planet orbiting around a red dwarf star, except it's not just one planet. It's actually 7 planets in a system. And I'll touch on the system a little more later, but the entire system is super compact. Basically, you have 7 planets that are all orbiting their star within the distance that Mercury orbits to the sun in our solar system. So the entire system is kind of like compressed in. And so as a result, if you were on the planet TRAPPIST-1e, all of the other planets in the system would loom really large in the sky because they're so close to you, right? And so these are different artists' renditions of what the planet might be like. They've taken some artistic liberties, but it's based kind of in fact, right? But obviously there's a lot of artistic liberties taken here. So I guess the summary of this is that Kepler mission and what we're starting to find with the TESS mission and all of the other spacecraft and ground-based telescopes that we have looking for planets have found this wonderful diverse zoo of exoplanets out there. We have gaseous planets, we have planets like Jupiter, we have planets like Jupiter that orbit super close, we have planets like Neptune, we have planets that are smaller than Neptune, we have even rocky planets, we have all kinds of planets out there. And we don't yet have a truly Earth-like planet in that like we have an Earth-sized planet orbiting a star that's really similar to the sun. But that's probably because it's just really hard to find those kinds of planets. So I'm going to go back to Gliese 12b real quick and go back to this graph of brightness over time that that I had a year ago when I started this whole project, right? So how did we use this graph of brightness over time to deduce all of the characteristics of Gliese 12b, and what exactly did we find? So I should mention that graph of brightness over time showed a few transits, but there was a lot of gaps in that data. So what we actually did not know when we first had the data for Gliese 12b was what is the orbital period. And that orbital period is absolutely crucial because if we don't have that orbital period, we don't know the temperature of this planet. So immediately, the first order of business was for me to go out and observe with Mount Kent, which is the telescope right here in our backyard in Toowoomba, and try to predict when the next transit was happening. So we actually thought that the transit had fallen in one of the gaps in the data. And so we could still make a prediction about when the next transit was going to happen. So I did the math. I figured out when the next transit was happening. We went out to Mount Kent. We made an observation. But one observation is probably not going to be enough. So some other members of my team basically proposed for various different telescopes. There was a spacecraft called Cheops that we used. There was a spacecraft called Cheops that we proposed for to observe this at the times that we expected the transit to happen. And there were three ground-based facilities that we used to measure the transits as well: Speculoos, the Purple Mountain Observatory in China, and Minerva right here in Australia. So we had 5 different telescopes at the end of the day observing this target to try and detect the transits, as many transits as we possibly could, so we could get really precise data. And it was a tremendous success. So we ended up working with people all over the world, in China, in the UK, in Australia, in the US, all to try and get these transits and to try and understand the characteristics of this planet. So with all this data, we do what you do in science, which is you write up a paper, you send it to a journal. The journal will give you a peer reviewer who's basically another astronomer, some member of the community, who will sort of read your paper through really thoroughly, will give you feedback and advice, and will say, yeah, we'll accept it for publication or we'll reject it, right? And if you get your paper accepted for publication, then you can consider it kind of correct science, or not correct science, because it can still be wrong even if it's in a publication, but at least it's been peer reviewed. So there's a degree of scrutiny to your work, and there's a like you can have a sort of correction for things that might have been inaccurate, right? There's a check. And so we published a paper, and that paper suggested something pretty interesting. So Gliese 12b is a tempered planet that's only 40 light years away. That actually makes it the closest transiting temperate planet that has ever been found to date. One of the more exciting discoveries with TESS, if I do say so myself, it's Earth size, so it's almost exactly the radius of Earth. It also orbits every 12.7 days, so about every 13 days it orbits its host star. So you might be curious why I'm saying it's temperate if the Earth orbits the sun every 365 days and this planet orbits its host star every 12.7 days. How is that possible? Yeah, as it turns out, the math works out so that if it didn't have an atmosphere, the temperature on the surface of the planet would be a nice 14 degrees Celsius, right? So this is what we call the equilibrium temperature. And I can go into that a little bit. If anyone has any questions about that, I can explain that a little bit more. But how is it possible for this planet to be temperate when it orbits that quickly around its host star? Oh, press the wrong button again. The question that a lot of you are thinking right now is it habitable? So this is a really tricky question, and there's a lot of facets to that question that I'll try to go into a little bit. But the first possibly the first check that you have to figure out if you were trying to ask if a planet is habitable is it in the habitable zone? So there's this habitable zone that we call around every individual star is a different habitable zone. It's that area around the star that's not too hot, not too cold, but just right. And that's why it's also called sometimes a Goldilocks zone. For stars like our sun at the bottom over here, our sun is called a G-type star. I should probably point with the laser pointer. Is that it? There we go. That's like a G-type star. And so that's a pretty middling star. And for a star like this, the habitable zone is around where Earth is, right? Of course, the Earth is habitable, right? For stars a little bit cooler than our sun, that habitable zone is also closer. It's like being around a bonfire. You can be reasonably far out and still be toasty. If you're around a campfire, you have to get a lot closer to be at the right temperature. And for cool red dwarf stars, which are the coolest stars, it's like a candle. You have to get really close to be at the right temperature. And that means that the habitable zones around these red dwarf stars are really, really close in. There's also something really important to mention about red dwarf stars. It's that they're the most common stars in our galaxy. So the questions about habitability around red dwarf stars are also really important, because if planets around red dwarfs are habitable, our galaxy's teeming with habitable planets. But if there's some catch there, if there's some reason why planets around red dwarfs cannot be habitable, we should probably know that, because that actually eliminates a lot of the planets in our galaxy from habitability contention, right? We know that at least one planet around a G-type star is habitable. It's our planet Earth, right? It is in fact inhabited. The other thing that makes red dwarfs interesting from the perspective of habitability is that they last a lot longer than planets or than stars like our sun. Our sun will last about 10 billion years. These red dwarfs last hundreds of billions of years, much longer than the lifetime of the universe so far. So we actually haven't seen a really cool red dwarf ever die in the history of our universe, right? That also means that if life were to exist, it has a lot of, on these kinds of planets, on planets around red dwarf stars, it has a long time to develop. It has a long time to exist, which is important. The catch is this little X-ray irradiance part, if you see that. Red dwarf stars tend to be really active. So Gliese 12 is actually a red dwarf star. That's why Gliese 12b, the planet, can orbit every 13 days and still be reasonably toasty, because Gliese 12 is a red dwarf star. Red dwarf stars have these problems of really high activity levels. They can flare, especially when they're very young. They can emit these X-ray flares that kind of blast planets around them. And this has been proposed as a possible problem for planets around red dwarfs being habitable. So it's also a problem from a technical perspective. Duncan mentioned the way that we try and identify these really subtle signatures of atmospheres around planets by, say, pointing the James Webb Space Telescope at them, trying to filter the light coming through the atmosphere and trying to get whether the light passes through the atmosphere or not. If there's star spots on your star, if the star is flaring during that process, it's going to drown out the signal from your atmosphere. So activity is not only just a problem for the existence of an atmosphere, it's also a problem for the detection of that atmosphere, because it drowns out that subtle signal. So red dwarf stars tend to be way, way more active than the sun. And that has posed a really big challenge to studying planets around them. I talked about the TRAPPIST system earlier. That TRAPPIST system has been really, really interesting from the perspective of astronomers, because those 7 planets, I think 3 of them are technically in the habitable zone of their star. And so, of course, one of the first targets for JWST observation was several planets in this TRAPPIST system, but there have been some obstacles in that, as I mentioned, it's a bit of a technical challenge to look at such an active star and try to detect the atmosphere of planets around it. TRAPPIST-1 is a great example of this because it's had trouble, JWST has had trouble detecting the atmospheres of the planets around these stars. And for the planets that it has observed, the first 2 or 3 planets so far, B and C, if I remember correctly, have papers out already. It has not yet found any signatures of an atmosphere. So it's not all doom and gloom, though, because Gliese 12b is actually one of the lowest activity red dwarf stars ever found. And so it's so low activity that if we were to point the James Webb Space Telescope, we would probably get a really good picture of what the atmosphere of Gliese 12b, if any, is like. And I'll cover that a little bit more later in this talk, but I'm going to quickly cover another interesting question when it comes to habitability. Some of you might not know this, but Venus is actually kind of a twin to Earth. It's almost the exact same size as the Earth. It's technically also within the habitable zone of the sun, depending on your definition of a habitable zone. But while the Earth is like a haven for life as we know it, it's a beautiful, nice, balmy temperature on the Earth, and we've got lots of water here. Venus is kind of the polar opposite. It's hellish, it's extremely hot, and there's no water, right? It's very inhospitable to life as we know it. There have been suggestions that there could be other kinds of life, and people have been trying to look for that, but there's no conclusive evidence of that yet. It's very, very different from the Earth, and that's something that we know for sure. So how did Venus come to be so different from the Earth? This is a really interesting question. I'm sure Jonty could answer a lot of these questions very well, but we actually don't have a very good idea yet. At some point in the history of Venus, it ended up having this, what's called runaway water loss. So all of the water, if there was any water on Venus's surface, just escaped into space. And the reasons for this are unclear, are like, there's been progress made to figure out why that's exactly happened, but it's pretty unclear. And for some reason, Earth managed to sustain all of the water, and as a result, it's really good for life as we know it. So when we're asking questions about habitability, there's a lot of different facets of this. We want to know whether planets around red dwarfs can hold onto their atmospheres in the face of the activity from these stars, right? We want to understand when and why planets lose their water, because it'll help us understand why Earth and Venus came to be so different in our solar system. And also what kind of planets out there might end up being able to hold on to their water. And then what kind of atmospheres are conducive to life? There's all kinds of atmospheres that we expect out there. We've seen different kinds of exoplanets have various different atmospheres, but from a solar system perspective, I think there's like basically 3 thick atmospheres in the solar system. There's Venus's atmosphere, which is quite inhospitable to life. There's Earth's atmosphere, which, as we know, is quite hospitable to life. And there's like Titan's atmosphere, which is a moon. And it also has a bit of an atmosphere, and we don't quite know whether it's conducive to life, but there's going to be missions to study that in the near future, which is quite exciting. But it probably, like, there's no obvious signs of life on Titan yet, so we would have to dig a little bit deeper to study that. Duncan already talked about the James Webb Space Telescope. It's been fantastic. Hubble has a 2.5-meter mirror. I should probably mention, I'm on a team that's actually observing Gliese 12b with the Hubble Space Telescope in a couple months. That's really exciting. What we're actually searching for with Hubble is signs of the runaway greenhouse effect on Venus. Sorry, not on Venus. What happened on Venus was the runaway greenhouse effect. We're looking for signs of the same process happening on Gliese 12b. And so if that were an ongoing process for Gliese 12b, we might actually be able to see signatures of that with Hubble. So that's the first round. We're also hoping to be able to use JWST to study Gliese 12b, because we would get an extraordinarily clear picture of what the atmosphere might be like. I told you all that it's only 40 light years away, and it's the nearest tempered transiting planet to the Earth. Why is that? Why is that special? It's not because we can actually go there in our lifetimes. In fact, there's no exoplanet we found that we can realistically go to in our lifetimes, because the distances in space are just far too vast. Even at the fastest speed that humanity has ever been able to travel at with Voyager 1, it would take hundreds of thousands of years to get even to the nearest star system, let alone a planet that's 40 light years away, right? So as a result, the value of it being so nearby is actually that we can point our telescopes at it and we can get a really clear picture of what the characteristics of these planets could be like. Not that we can actually go there. But this is really, really valuable, because if we point a telescope like JWST at Gliese 12b, we can distinguish between, if it were to have an Earth-like atmosphere, we would be able to tell that it's different from a Venus-like atmosphere or a Titan-like atmosphere, or various other different kinds of atmospheres that we don't even know about yet, right? So Duncan already talked about the method of transmission spectroscopy, which is where you look at the signatures of light transmitting through the atmosphere of a planet, and the planet kind of looks bigger in colors where the atmosphere is absorbing that color, right? And it looks smaller in the colors where the atmosphere is not absorbing that color. There's also another technique that you can use with JWST. JWST is kind of like a really, really good infrared camera. So if you look at the end, Duncan's nicely provided an infrared camera for us all to try out, and showed us pictures of his cat with the infrared camera. Well, as it turns out, at 14 degrees, Gliese 12b is expected to be only slightly cooler than a cat, which means that you can point a particularly sensitive thermal imaging camera, an infrared camera, at it, and literally just see the light coming out of this planet, right? This is called emission spectroscopy. If you were to split that light up, you can get a spectrum of the planet literally emitting light, right? And this is another technique that you can use in tandem with transmission spectroscopy that JWST is expected to be really good at. So we're also proposing to make an observation of Gliese 12b with emission spectroscopy as well as transmission spectroscopy. This is one of the few targets that is actually really good to be done with both. And hopefully what we're trying to figure out here is, so one thing that I didn't mention earlier is Gliese 12b is kind of positioned right in between Earth and Venus. Earth has an insolation of 1 times like Earth insolation, right? It gets the amount of light that Earth gets. Venus gets around 1.9 times the amount of light that Earth gets in our solar system. And Gliese 12b gets about 1.6 times the amount of light that Earth gets. So it's kind of right in between Earth and Venus. So it can help us figure out why Earth and Venus came to be so different, because it's right in between them in terms of its temperature, right? So the artists that created all of the art for Gliese 12b for the NASA feature depicted Gliese 12b with 3 different kinds of atmospheres. Like on the left here is Gliese 12b imagined with no atmosphere. This would happen if its atmosphere has been blasted away by its host star. Something like maybe Mars in our solar system also has a very thin to no atmosphere. In the middle, if it has an atmosphere like the Earth, right, like reasonably thick atmosphere. And if its atmosphere is too thick, if it's very like high density, right, you'd get an atmosphere like Venus's, right, that looks something like on the right. And we don't know what the answer is yet, but with observations with JWST, we can actually figure out the differences between these 3, and Gliese 12b is an excellent candidate for being able to do this kind of thing. So I'm going to conclude with something that I think Duncan touched on in his question and answer session, but it's called the Drake equation. I would be remiss to not mention this in a talk that touches on habitability. The Drake equation is more than just habitability. It's specifically referring to not just habitability, but also our ability to communicate with intelligent life, right? It's not just about bacteria or like single-celled organisms. It also has factors in it that relate to civilizational communication and how long civilizations last. But what we're interested in from the perspective of exoplanet science right now is the parameter over here, n sub e, right? The average number of planets that can support life in stars that have planets, right? And then out of that, we can possibly, in the near future, we might be able to also measure something like this, the fraction of planets that actually develop life. And this is, Duncan touched on the idea of measuring disequilibrium biosignatures. So what that means is we're looking for gases in the atmosphere, for instance, that are out of equilibrium. Life tends to pull its conditions around it outside of equilibrium. For example, the amount of oxygen in the Earth is suspiciously high. If we were to look at the Earth with the James Webb Space Telescope, if we were aliens looking at the Earth, we might notice that the amount of oxygen in the Earth is suspiciously high. And if there wasn't something continuously pumping in oxygen into the Earth's atmosphere, it would probably dissociate and oxidize various other species and basically go away, right? So the amount of oxygen in the Earth's atmosphere is actually in disequilibrium. And this is a possible hint that there could be life on the Earth, right? And so we're looking for these kinds of things on atmospheres other than the Earth, and they could be signatures of life. So for the time being, the only two parameters that we can really get a handle on observationally for the foreseeable future is N sub E and F sub I, which are F sub L, sorry, which are these two parameters of the Drake equation. And with I guess developing technology, we can go further and further down the line until we can get a good handle on the entire Drake equation. But Gliese 12b kind of proves that it's N sub E. It is possible that the number of planets that can support life, if we found a planet that's 40 light years away, possibly temperate, it just gives us a hint that the number of planets there could be actually quite high. Yeah, I'm happy to take questions about this.
To share. Brilliant. So we've got time for some questions in the room. And Carolyn's already running up to the back to get the first one, which is really good. And we'll again take questions in the room first and then see if there's any online.
How would you be able to detect if there's life potentially, if it's at the phase of when the dinosaurs were still like not intelligent, but large living things?
Yeah, so that's a great question. We wouldn't necessarily, I don't think we have the technology right now to be able to figure out if there's like large organisms on a planet. What we're looking for are these signs of disequilibrium chemistry. So right now, all we can do with JWST is look at the atmospheric composition of planets and try to figure out if there's something out of whack, if there's something that's not in equilibrium, right? And that could be a suggestion that there's life. But disequilibrium chemistry alone, in my opinion, can't really conclusively pin down the existence of life. So you need to use it with other techniques and more advanced methods to be able to really prove that there's life. But disequilibrium chemistry is definitely a great hint that there could be life.
Mm-hmm. The next one was a little bit down here.
When you said that, the atmosphere is very oxygen rich, but wouldn't life would have originally developed in water instead, which then would have developed, the atmosphere because, the single-cellular life, formulated oxygen. But a lot of planets wouldn't be capable of supporting life due to the fact that light itself is a laser and it would deconstruct any form of life. So you need somewhere that's dark but also warm, like geothermal vents on the bottom of the ocean floor, for example, that's able to apply constant heat that forms your basic molecules to become more complex and then be able to. Sorry, I'm rambling.
No. There was a couple of good questions there, like life starting out in water. I think Jonty probably knows more about this than I do, but there's a significant fraction of the modern Earth's oxygen budget that's delivered by cyanobacteria that are actually in water. So even if life comes from water or if life originated in water, it would still be able to contribute to the atmospheric composition of the planet as a whole. And I guess the second question is, as I think photosynthesis is kind of like how at least a lot of the atmosphere has been changed by organisms on the Earth as we know it. So light is kind of required for photosynthesis to operate, but people have speculated about extremophiles and different kinds of organisms that don't require light in order to like photosynthesize and instead get energy from geothermal vents and other kinds of things. So like there could be life that's different from how we know it, and that would be causing different kinds of disequilibrium, and it would be interesting to look at that as well.
The reason why I say that is because I would assume that, how adaptation occurs when you grab an organism and you throw it into a completely different environment, the chances of its survival gradually become zero. But when you gradually change the environment, then the adaptation then occurs.
Yep.
So when you said about photosynthesis, it's because over time they'll be able to react with the light around them, which then allows them to, actually process it instead of just instantly put it in the, fire.
Yeah, you're right. Yeah.
Yeah, I mean, I think part of the challenge with all this, I think the next question I saw was the gentleman with the blue shirt, actually. So I'll speak briefly while Carolyn moves over. Part of the challenge for all of this search for life stuff is we've only got one example.
Yep.
Life on Earth's very diverse, but it's one example of one origin of life. And so drawing any conclusions from that beyond simply the fact that life can exist is you run the risk of becoming very Earth-centric in your thinking. And that's why rather than looking for geothermal vents, or looking for oxygen, we're keeping our minds open and just looking for something out of place. And that way, we'll know it when we see it, but we don't know what it'll be until we see it, essentially, if that makes sense.
Absolutely.
But thank you.
Why do red dwars last so long if they're so high activity? And how do we know that they last that long if we haven't existed that long?
Yeah, that's a great question. It has to do with how much energy they're putting out, right? So stars are like you might have heard of the analogy that stars are like rock stars. The largest ones live fast and die young, right? Like the hottest stars, O-type stars or B-type stars, are burning through their fuel source, which is their mass, at a tremendous rate, and they're putting out a lot of energy. But that also means that they're burning through their fuel source very quickly. Whereas the coolest stars are not putting out a whole lot of energy, so they can last a tremendously long amount of time, right? And so that's how we know that red dwarf stars last a really long time, because basic physics actually tells us that based on the amount of energy that red dwarf stars put out, their fuel stores will last an inordinately long amount of time, whereas our sun will burn through its fuel source of fusing hydrogen together in about 10 billion years or so. Mm-hmm.
All the high activity stuff is not very energy intensive.
Yes, that's right. So the high activity is basically like flares or these X-ray bursts that come out of the star, kind of like the stuff that causes aurora in our night sky on Earth, right? That happens a lot more often, especially for young red dwarf stars. But that doesn't actually, it's not a significant part of the energy budget of the star as a whole. So even though it can be really damaging to atmospheres of planets around those stars, it doesn't compare to the amount of total light that a star is outputting throughout its entire life.
I think we'll take one more question from the room, John, over there. For the other people in the room who've got questions and I've not seen you put your hand up, please grab Shashir when we finish afterwards. And just before John starts mentioning aurora, there is an aurora alert out for tonight because there was an enormous solar flare about 24 hours ago. The odds of the aurora being visible from our latitude is incredibly small, but there is a chance with this one, but it's a very small chance. Probably looking early hours of the morning. Probably not going to see it, but you never know. So I just want to flag that up because this one is big enough that there is a chance. It's just a small chance. Anyway, sorry.
Cool. We're always looking out to see if we can find something there. Mm-hmm. With the changes in technology, is it potentially possible to use something like entanglement to see if people are observing us? And do the whole lot at once.
Yeah, that's it's very difficult for me to speculate on something like that. I would say the chances of that are pretty low. The ability for us to measure stuff out there is always going to be easier than for us to be able to figure out whether other people are looking at us. It is something that SETI, is an organization devoted to the search for extraterrestrial intelligence, does think about. They do think about some of these more out there ideas from the perspective of a scientist. and they do different searches of technosignatures, which are signs that like technologically advanced civilizations might exist. And I know that they have thought about some of these ideas of like whether other civilizations could be observing us and whether that has signatures. But for now, that remains pretty firmly rooted in the more out there category. Most of the efforts of scientists are dedicated to try and finding signs of more basic, more primitive life on exoplanets than there are for people looking for technosignatures or even like signatures of intelligent life looking at us. Yeah.
Brilliant. Well, we'll hand over. We again have no questions from online, which is all good. So what I might do here is bring the formal proceedings to an end and give you a chance to come and talk to our speakers in person rather than shouting down. But please, can we, before we do, thank our speakers again? Thank you. So I will flag up, as people feel free to come down, that we have another session tomorrow evening when we've got one talk, and then if the weather is kind to us, we'll do a cross and actually do some observing from Mount Kent and take some pictures. And on Saturday afternoon, we will do a session where kids can ask questions just like you have been just there of our panel. So that's the schedule for the next couple of days. We do also have, I want to flag up to everyone, a bright comet, not visible tonight, but will probably become visible in the evening sky early next week. I normally wouldn't flag something up like that in a situation like this, but it's the best comet I've seen since 1997, and probably the best one we've had around the globe for at least a decade. So it should be quite good in the evening sky just after sunset early next week. And I will probably mention that again tomorrow because I'm really excited, so I can't stop talking about it. Thank you all very, very much, and please feel to come free and come have a chat to people and have a look at the experiments. Thank you.